Hello friends and welcome to a lecture on numerical computation methods. Today we will solve a second order differential equation using Sympy, which is a library, a very powerful library in Python. It's different from the tutorials that are available on this topic on YouTube. Here we will be using Sympy and we will be generating the analytical solution as well as the numerical solution. So it gets very interesting. Okay, so stick around and have a look. For this, first you have to install Sympy. Now you can have a look elsewhere in the playlist here that how do you install Sympy if you want to install it in Python. So in my machine, Sympy has been installed. So I will go ahead with importing it. So you write import Sympy and then from Sympy, import star. So this imports all the functions in Sympy. Now what do is we write variable as x. So this defines in single quotes. So this defines x as the variable. Also we write y is equal to function to start with y. Okay, and we just see the output of y. Now it has defined y as a function. Now if I just add here x, now this defines y as a function of x. Now what does this mean? I can take y and then I can write diff, that is differentiate with respect to x, and gives me dyx by dx. Okay, so it has differentiated it with respect to x. Right, now the same thing can be written also as derivative y x. Now this does the same thing. This also gives me the same thing. Now let's start with writing the differential equation in the symbolic form. So for this we write SODE, that's a variable. We define SODE, a variable which will store the differential equation in a symbolic form, and then we write y, that is derivative. The first term of course is derivative of y with respect to x, and with respect to x we can also write it as x comma 2 plus derivative of y with respect to x minus 6y. So let's run the kernel once again. Yes, we are done. So let's look at the differential equation. And there we have stored the differential equation in the symbolic form in SODE variable. Now it's very simple to solve it, and you will be very surprised to see that. If you want to have the solution of this, just write SOLN solution, which is a variable which would store the solution, and write dsolve, and then write the name of the differential equation that you want to solve, that is SODE, with respect to which variable you want to have it solved. So that is y, and enter, and the solution is done. Now let's have a look at the solution. And as you can see here, the general solution is there. Now what if we want to find a particular solution to this problem of differential equation? Now we all know that to get a particular solution, we have to give either the initial conditions or the midpoint conditions or the endpoint conditions, which are known as boundary conditions or midpoint conditions. So in a problem, We have already taken the boundary condition as y at x is equal to 0 as phi and dy by dx at x is equal to 0 as minus phi. Now, how do we put this in this particular step and get a particular solution? So for this, what we do is, let me come back here. Let me insert a cell above this. So what I'll do now here is, I'll write initial conditions is equal to, and write a dictionary. So in the dictionary, we write y dot subs, that is short for substitute, at x is equal to 0 is 5, and also y, the differentiation of y with respect to x at x is equal to 0 is equal to minus 5. So here we have stored the initial conditions in the dictionary. Now what we do is, we write ICS, short for initial conditions, equal to the initial condition. Run it. Okay, it was initial conditions S. I have missed S. So let me put S here, run it. And you will find that you get a particular solution. Isn't that great? So now let's get ahead with finding the numerical solution to this. So all we have to do is write SOLN dot RHS first. Now this is only for demonstration that I have done it. So this effectively takes the right hand side of part of the solution, which actually is the solution part of it. Yx is nothing but, it's just the variable. That is the variable y. Variable y, which is a function of x, is equal to 2 e raised to 2x plus 3 e raised to minus 3y. So the RHS is actually the function part of it. Now, if you want to find the value of this at, let us say x is equal to 2, we write SUBS x comma 2. So it calculates the RHS at 2. Now, what if we want to find the numerical value of it? We just write FLOAT float and we are done. So we have the numerical value of the solution of the differential equation at x is equal to 2. What if we want to plot it? So as I was just saying, we need to plot this function. So how do we do it? It's pretty simple here. We write plot and we write SOLN dot RHS, because the RHS part is something which has the function and it can be plotted for various values of x. Now, here the domain arbitrarily has been taken from 10 to minus 10. Now, what if we want to study this function at different domains, or we want to particularly study this function in this domain itself, that is 0 to 10. Now, how do we do it? So there's a way out. So what we write here is write x lim is equal to, before that, let's do something. Let's remove this, run it, and let's see what is the range of the function. Okay, so that is going to be an important thing. So we write SOLN dot RHS dot SUBS. So the domain that we were interested in was 0 to 10. So let's take the value of 10. X is equal to 10 and see what is the value we are getting. Okay, so let's run this once again. Run all. Okay, there we are. Okay, so to find the value of this, if we write FLOAT float. Oh, that's a pretty big value. So that's units, tens, hundreds, thousand, 10,000, then 10 raised to 6. So this is 970 into 10 raised to 6. So we can slightly narrow ourselves down. So we narrow it out. So we write till 7. And that's a pretty cool value. Okay. So we store it up. We store it as A. So let's store it as a value. So we write DOM range, RANGE range upper, UPPER upper is equal to, so that's going to be the upper range of the function. And of course, the lower range of the function is going to be range lower is going to be equal to float x0, right? So here pretty much we have got the range of the function now. Now we can replot it by writing plot solution dot RHS. So the x limit, that is the domain, x limit is nothing but the domain. This is entered as a tuple. So we have to put it in square brackets where the first entry is going to be the lower range and the last entry or the next entry is going to be the upper range. Upper domain, I'm sorry, 0 and 7 are domains. And then afterwards, y lim is going to be the equal to, this also is entered as a tuple. This is going to be the lower range. So we write RANG range lower, comma, RANG range upper. Right? So square bracket complete and we are good to go. And there, as you can see here, it has plotted it. And we have studied, or we have the plot of the function from a domain of 0 to 7 and for the entire range that we want, right? So this is a way of plotting it. Of course, you can use matplotlib also. I'll shortly demonstrate this now after this. So I was discussing about how to use matplotlib to plot this function, and it has obvious advantages which you'll have we'll be looking into it in a short while now. So for this, we first import NumPy library, import NumPy as np. Fine, we are done with that. Now we write xval is equal to np dot lin space linspace 0 to 7. That's our domain, and we need 100 values of x in this domain. So let's see what have we got as an output of this. So we can see here that we have got equally spaced 100 values between 0 to 7. Okay. Now what we do next? We write plot function is equal to lambdify x comma soln solution dot RHS. Okay. Now what has this done is this has lambdified the solution dot RHS. What was now a symbolic expression has now been converted into a function. So what does it mean now? Now if we write plot func func at 2, it'll calculate the value at 2. Initially what we had to do it, we had to give solution.rhs.subs, right? Now here directly it has been converted into a function where if the input is given, the output is automatically calculated out. Now what if we want to make this a numpy, or that is an array function? And in an array function, what can happen is you can give an array as an input and you'll get the values, array values as output. So what we do is we just write numpy here and it's done. Now, if I give the values of x here, xval, it calculates the value of some solution dot RHS at all values between 0 to 7. So with this, we can get ahead now. What we can do is we can write plot plot func func values. So write val is equal to plot plot func func x val. So now it has stored the value of solution dot RHS in this at all the values between 0 to 7, all the 100 points, right? Now we can go ahead and use matplotlib. So for this, what we do is we import mat okay, so we have imported the matplotlib function. Now here what we write is plt dot plot x val comma plot func function val. Oh, so there we see we get a very neat plot here. And why is this plot much more smoother as compared to the previous plot? Well, the reason is pretty simple. We have calculated the values of the function at 100 different points here. Now, what if we want to plot this function using matplotlib, which is a very common plotting library in Python? Now, it has its own advantages, and I'll demonstrate how to use it. So first, what we have to do is we have to import numpy as np. Okay, so we do that. Now we write x val is equal to np dot array. You'll shortly come to know what does this mean. We take a value from 0 to 10. Okay, so we had a range from domain from 0 to 7. Let's take that as 0 to 7, and let's take 100 points in between 0 to 7. Now what does this give you? Let's see the output of it. It gives you an array from 0 to 7. Okay. Now let's see what are the advantages of plotting it in matplotlib, or the function that we have, or the library that we have just used. We can write plt dot x label label as x, then follow this by plt dot y label as y, y. Well, we can put it in double quotes too. Single quotes or double quotes, it really doesn't matter. So let's put it in double quotes itself. And then we write plt.grid grid and run it. And as we can see here, the x-axis has x written to it, the y-axis has y written to it, and we have a grid which makes it very easy to read it. And can we copy it? Yes, we can copy it. We can always copy the image and paste it in any document that we want, and it gives us a very neat figure in the output. And of course, a lot of embellishments can be done to it, which I leave for you to discover. So that was all about how do you solve a second order differential equation using Sympy. Now this, as you can see here, has an advantage. It gives you an analytical solution. And that analytical solution can be again used to plot the graphs. So this obviously has advantages when one wants a closed form solution to the problem that we have, and he wants to really analyze it off, So a closed form solution sometimes is required in many places. When you're writing thesis, people insist, okay, if you have a closed form solution, it would be nice. I'm not saying that, and not having a closed form solution and having the plots just using SciPy integrate OD int, which just solves it numerically. Yes, one can quickly work with it, and one can always get the nature of the graph. But here what happens is, because you get the solution in a closed form, a lot more research can be done on it. Okay, so that was all about it, friends. Do write your comments. I eagerly look forward to reading your comments on my lectures. And if you find it advantageous, you find this lecture is of real advantage, of real value to it, do forward it to your friends. And yes, do subscribe my channel and keep viewing. Goodbye, friends. Good evening and have a great day.